So my name is Andrea. I'm with the excuse me, construction solutions team with Nucor. I'm joined today with representatives from the Seattle mill that we have, and also our environmental specialist from corporate. So we'll just dive right in. A quick intro to who Nucor is. We are the largest steel maker and steel product maker in the United States. We have 24 beam mills all over the country, and in addition to steel shapes, we have a lot of steel products, including prefab buildings, fasteners, foundation sheet piling, metal deck and joists, etc. Traditionally, we would be interacting with our customers who are steel fabricators and other material procurement teams, but we've recently developed the construction solutions teams to interact with the design community to bring our knowledge about steel to the people who are actually specifying it. So we're excited for this opportunity to speak with this group here today. I'm based in the Los Angeles, Orange County area, but my team is across the entire country because we understand that construction varies all over the place. So as we learn from the different pain points and successes that people are facing across the country, we hope in turn to be able to use that information and continue providing better steel for the construction industry. So today we'll be going over, as Shana mentioned, just how steel is made and what was the impact of that to embodied carbon, and just a couple of other topics then for when you are designing, how to understand the information that's provided. So my teammates with me here will chime in at different parts of the slide, and we're happy to be in touch with everyone afterwards if you have further questions. So steel making all starts the same way, whether you are talking about construction materials like beams, joists, deck, or even the steel we see around us in cars, appliances, anything that's steel. There are two main ways of making steel, as you can see here, the basic oxygen making method and also the electric arc. We'll dive specifically into those in a second, but just to give a broad overview, steel, once we get molten steel, it all gets refined to the correct specification and material properties that we're looking for, and that gets continuously casted. In other words, that gets made into these long prismatic shapes, whether they're blooms, billets, or slabs. This is like the pre-steel, if you will, for a lot of very varied end uses. So these semi-finished products will then get reheated and rolled. This is where we get the term hot rolled steel shapes. And then in the construction industry, that will go into either long products. So this is your rods, your bars, including rebar, or sections such as wide flange, channels, angles, or your flat products. So you have plate products or hot rolled coil, which in construction gets further worked into light gauge material such as metal deck or metal studs, or in a tube mill to become our tubular products, which is HSS. So there are other value add processes to transform the steel into the other products, whether it goes into manufacturing or appliances, or even other products in the construction space. But pretty much all steel starts with these initial steps. So let's go back to those two main ways of making steel. The first one is the basic oxygen furnace. This is found in an integrated mill. And the photo we have up here is of a steel mill in Inner Mongolia, China today. This is probably what a lot of people think of when they think steel making. It's a dirty industry, lots of pollutants, and let's get into what exactly it is. So the BOF process has primary inputs of iron ore, coal, limestone, and some scrap. So it could go up to 20 or 30% recycled content. But mainly this comes from raw materials that gets, as you can see in the video here, put into a furnace that then adds oxygen to work those materials into molten steel. A lot of times these plants are coal powered or can be electric powered as well. But the main thing about the basic oxygen furnace is that the previous step to it, the blast furnace, which processes all the raw materials, poses a lot of environmental hazards. In the past century, this one step alone has been responsible for 4% of global greenhouse gas emissions. So overall, this process has a carbon intensity of 2.15 tons of greenhouse gas per ton of steel made. And this type of steel making is about 70% of our global steel production. On the flip side, we have the electric arc furnace technology to make steel, and this is found in mini mills. The photo that you see here is a familiar sight to many of you. It is our Nucor Seattle location, and this is actually a steel mill in Seattle. Just visually, you can see that this process is a lot cleaner. So let's get into why that is. So the primary input for EAF, as Shana mentioned, is scrap steel. So this makes it a highly recycled product. On average, EAFs use 48–50% steel, but that number can go as high as over 90%, which we'll talk more about when we discuss our Seattle mill specifically. In addition to scrap, depending on what the final product type of steel that we're making, other supplements can be added to help with that chemistry. But in general, this is a recycled product. As the name suggests, it's powered by electricity. And mini mills are very economical where electricity is plentiful and there's a reliable and well-developed electrical grid. In general, it requires less energy and less manpower for higher steel output with an EAF. So this is 30% of the global steel production, but domestically, that number jumps up to 70%. And when you compare the average carbon intensity at 0.48 tons of greenhouse gas per ton of steel, that is less than a quarter of what happens in a BOF technology mill. So here at Nucor, all 24 of our mills are using EAF technology. So that's something that we are very proud of. I'm going to now hand it over to Ken. He is our sales manager in the Nucor Seattle mill to talk a little bit more specifically about their location.
Thank you, Andrea, and good afternoon, everybody. My name is Ken Bowden, and I'm the sales manager here at our Nucor Steel Seattle facility. Before we get into this, just real quick, there was a question on the chat that asked about DRI. DRI is direct reduced iron. It's a way to bring virgin material into the recycling process to give you better steel properties at the end of the day. We don't use that as 100% or a large portion of what we do across Nucor, but it is a way to bring some refinement into the steel process. So of course, any other questions, please feel free to ask. So I only have a couple slides here just to kind of highlight and talk a little bit about our facility. So this facility has been here since 1905, been here for a few years. Today in our current footprint, we are mainly a rebar facility that represents about 85–90% of our product offering. The other smaller portion of products that we offer are angles, channels, flats, and kind of a core grouping of merchant products, these structural sections. The electricity source here, of course, steel mills are very energy intensive. And so the majority of, 100% of the electricity used in our steelmaking process here in Seattle comes from Seattle City Light. Seattle City Light has been carbon neutral since 2005, and they achieved this, of course, by using hydroelectric dams and carbon offsets for any small amount of electricity on their grid from anything other than a hydro dam. So that allows us to use this in our process to have a very low carbon footprint. Furthermore, the steel that we make here, officially, we're at 97.4% recycled content on our recycled content lead letters, but in reality, we're over 99%. Everything that we do here is run from scrap, and the only virgin material that goes into our steelmaking process is the alloys, the lime, the carbon, the manganese, the very small amount, the 0.6% is what we use from a virgin aspect. The rest of it, it's all recycled. It has actually been, since 1905, Washington's largest recycler. Next slide, please. All right, so this is the last slide for me, but here we're extremely proud of this facility and what we do. And we do a lot of great things across all of Nucor, all of our mills, but this specific one to be oriented here next to Seattle. We have a site-specific EPD, which you can see the numbers, and this mill probably has the best carbon footprint EPD numbers in the entire world. And it's because the efficiency that comes with the type of mill that we are, the electric arc furnace technology combined with the hydroelectric energy source gives us incredibly low carbon footprint numbers. Furthermore, declare label available, red list free, LEED certification, etc. And like I said, we're very proud of what this is, where we are oriented in the country. And thanks again for having me and being part of this conversation. Thanks, Andrea. I'll hand it back over to you.
Great. Well, we're going to actually have Raleigh join us. She is from our corporate office with a focus on our sustainability team, and she's going to just share a little bit more about Nucor and our company's focus and goals in the sustainability world.
Yeah, hey everybody, Raleigh Sauls here, environmental engineer from our corporate office. And I do want to talk about sort of Nucor as a whole. We realize that being one of America's cleanest and most efficient steel makers is not enough. This year, Nucor committed to a 35% reduction in our steel mill Scope 1 and Scope 2 greenhouse gas intensity by 2030. And that's measured by our 2015 baseline, which is the Paris Climate Agreement year. This graph shows how Nucor stacks up against the world with regards to greenhouse gas intensity for both Scope 1 and Scope 2. You can see on the far left, Andrea showed us a picture of a China blast furnace earlier. Theirs is about 2.30 metric tons of CO2 per ton of crude steel produced. And then you see a blast furnace, moving on through India, Brazil, you see the global average at 1.69. We keep going down to the EU, United States without Nucor. Nucor is the largest EAF manufacturer in the US. And then on down to Nucor today at 0.47. And then with our 2030 goal at 0.38. And that 0.38 is 77% less than today's global average and 82% less than today's blast furnace average. So again, our 2030 goal is 77% lower than today's world average. And this kind of shows that similar story, but in a different way. You can see there in the gray on the top left, that's the average carbon intensity for a blast furnace. And then on the right-hand side there at the top of the blue, you see where the Paris pledges are, the 2-degree scenario, the below 2-degree scenario. And then if you look to the left of that on that green line, you see where Nucor is at now, and then where we're going with our 35% reduction by 2030. It puts us 18 years ahead of the below 2 degrees scenario goal. So Nucor continues to lead the industry in sustainability, and here are a few examples of that. As far as renewable energy goes, we are the 7th largest corporate buyer of renewable energy in the US. And in fact, this year we announced 2 VPPAs, or virtual power purchase agreements, where we are directly supporting the development of more than 350 megawatts of new clean energy infrastructure. And that's both solar and wind. We're all about efficiencies. Of course, there's energy efficiency, but also through the production of advanced high-strength steels. And those are a key component in building greener vehicles, but also in greener construction. And then we talk a lot about the circular economy. And Nucor is a pioneer in circular steel world. And in fact, for 10 years now, we've had a closed loop recycling process with one of the leading automotive manufacturers in the US. And then finally, on research and development, we're exploring a variety of innovative solutions, including carbon sequestration at one of our direct reduced iron, or DRI, facilities.
Thanks, Ollie, for walking us through just what Nucor has been doing and leading the sustainability front for the steel industry, really. So I want to touch on a couple of things now that specifically in the construction world, we can be focusing on and utilizing to reduce the embodied carbon in steel construction. The first, which Shana touched upon, is using higher strength materials. Nucor is excited to be domestically producing what we call AEOS steel. This is A913 specification steel. We are the only domestic producers of this material, and it comes out of our Nucor Yamato mill in Arkansas. So AEOS 65 is an A913 steel with higher strength at 65 KSI compared to the commonly found strength of wide flange at 50 KSI. So this higher strength is due to a quenching and self-tempering process that is at the end of the beam line. So if you recall early in those diagrams, when a billet or a bloom gets rolled through, it gets rolled through a bunch of stands to achieve its final shape. And at the final shape, like at the end of that line, we have the tooling to be able to then quench the steel, to cool it down quickly with water, and then allow the retained heat inside to then reheat the section or self-temper it. So this is all per the ASC, the specification, the ASCM specification, and it's something that we're happy to be able to provide domestically. So when it comes to designing, if you're an engineer on the call, I would like to share that this material has already been approved in the seismic manual, as well as AEOS D1.1 covering welding. So there aren't any extra hoops you need to jump through to use a higher strength. And because of its higher strength, the natural application would be some tonnage reduction in columns. We've seen up to 20 to 25% reduction in column size simply because you have more strength per unit of section. And also, there are some other benefits, such as a reduced requirement or eliminated requirement for preheat in the shape. So that means even outside of the embodied carbon perspective, when it becomes, when it's in the fab shop, there are savings from time and energy due to those reduced requirements. Not to get too technical into it right now, but there are some limitations in the size availability just due to that quenching and self-tempering process. So if you are interested in using this higher strength material and want to know more about it, feel free to reach out to me about it later on. One project that is in Seattle that has utilized this higher strength material is the RANIER Square Tower. AEOS was used for all of its columns. So that definitely helps, especially for such a tall structure that at the base, usually those are pretty heavy columns. By switching to grade 65 steel, you can realize up to 20-25% savings in those column weights. So it's exciting to know that this tower could be built with domestic steel, and by reducing that tonnage in steel, you are directly reducing your embodied carbon. I'm going to kick it back to Raleigh. She's going to share about another exciting way that embodied carbon can be lowered through using Nucor steel.
Yes, we recently launched Econic, actually. It's the world's first net zero steel at scale. And Econic is unique because it's a certification and not a product. So it can be applied to any product coming from one of our mills. And we see this as Nucor taking an active role, resulting in greening of our electrical grid. And I'd like to go back to where I mentioned earlier about the 2 VPPAs, or virtual power purchase agreements, that we signed into earlier this year. The RECs that we receive off of those VPPAs, so renewable energy that we have financed ourselves, are what's used to offset our Scope 2 emissions for Econic. So we are directly adding renewable energy to the grid. And this, and the unique thing about Econic too is it's not just a, it's a product launch, it's a cool product, but it was a customer-driven initiative from a big customer of ours, specifically GM. They'll be the first to receive that. But we see ourselves a leader in the sustainability world, but a lot of what we're doing has been customer driven. And I think that's a unique part of the products that we have. I see there was also a question in the chat about the grid mix for our US mills and then site-specific EPDs. We do have quite a few EPDs out there. We actually had 2 approved today, one for joist and one for deck. So they're not up yet, but we just got them. And on Nucor.com, on our sustainability page, we have our EPDs up there. Our EPDs are product specific. And then as far as the grid mix goes, for Seattle, we use Seattle City and Light. Most of our mills use an E-grid factor, and we use the E-grids from the US EPA, or Environmental Protection Agency. So those are pretty easy to access.
Ollie, I can answer these other two questions if you want, just real quick.
Go ahead.
It was the next question was the availability and lead time on the AEOS product. And because AEOS is just a end of process at that operation, it is the lead time is no different than any other product. It's just how we finish the product out. And that kind of goes into the last question, is the energy intensity of the process. There's really no difference in the energy consumed, the electricity or gas, et cetera, and reheat. It's all about the way it's quenched and tempered, which is adding the water at the end of the line. So it does not change the carbon intensity at all. It just is a way to increase the strength of the steel, which then in turn, of course, using less steel, no change to the carbon intensity is overall a net win for the carbon.
Yeah, I just want to elaborate on that. This is the next topic we're going to get into, is taking a deeper dive into steel EPDs. But because that AEOS steel is produced in our Yamato mill, and we have a Nucor wide flange specific EPD, that would be covered with that EPD as well. So the last thing we want to discuss is just the embodied carbon documentation, or EPDs, and specifically taking a look at some nuances in the steel EPDs. So the first thing I just want to go over quickly is, in a steel EPD, what can you find? What I've pulled up here as just an example is our specific fabricated hot rolled structural steel section EPD. So the first thing you can find, obviously, is the producer, us Nucor, but all between our two beam facilities. So there's Nucor Yamato, which I mentioned earlier, and Nucor Steel Berkeley, which is in South Carolina. You'll also note that for steel EPDs, it's important to take a look and see, is it a fabricated or non-fabricated EPD? In this case, for the wide flange, this is a fabricated EPD, and we'll get into where that plays a role in a second. So moving further in the EPD, I'm sure most of you are familiar with seeing this, but here we show the main thing that people are interested in looking for, which is the GWP. And in the EPD for a fabricated section, it will break down what then is defined by A1, A2, and A3. If something is fabricated, then pretty much A1 is how is the steel made. So the materials of the steel, the furnace and melt shop operations, how it's casted and then rolled, that's all captured in A1. Then A2 would be the transportation to your fab shop. And then A3 would be the fabrication itself, or the manufacturing then of this product. So for our EPD then, A1 is a number that is completely controlled by Nucor. This captures our operations at the steel mill. And then A2 and A3 rely on industry averages. As you can imagine, like, we're not feeding just one fabricator, but many different fabricators. And the fabrication portion obviously depends on the fabricators themselves. But to make this EPD, these are average numbers. To compare that with a non-fabricated EPD, this is an excerpt from our Seattle EPD, which is a non-fabricated bar EPD. So the overall takeaway when it comes to fabricated versus non-fabricated is to make sure you pull up the EPD itself, because the EPD will give language to clearly define what is captured in the GWP and other numbers. So here, if you read through, it says that it's a cradle to gate life cycle, gate meaning the gate of our mill. So it will define A1, A2, and A3 as what happens within the mill. And I just want to reiterate how important it is to read through this, because even though there's the same A1, A2, and A3 categories in the fabricated EPD, how those things are defined are slightly different depending on what the EPD is for, fabricated versus non-fabricated. So takeaway, read the EPD. If you pull something out of EC3 or Tally, it's always good to try to find the actual source instead of just looking at the number that's pulled up in a database, so you can really see the full picture of where that number comes from. So then I think that this begs the question of, if you are looking at a fabricated EPD, but you're only interested in a non-fabricated number, how do you get that? In the Nucor Beam EPD, it actually provides a cradle to gate mill product number. It also breaks down specifically between Berkeley and Yamato, what happens at the two mills. But this cradle to gate number, you'll notice, hey, why is it slightly lower than the A1 number? Because didn't I just say A1's completely controlled by us? So A1, because this is a fabricated EPD, will include the scrap that's generated during fabrication. So we understand we'll sell this much steel to a mill, but some of it does become scrap because not everything is used for that final fabricated product. So this cradle to gate number removes 7% from the A1 number to truly represent then what our mill is doing, and it tries to balance out the fact that we're incorporating industry average numbers for A2 and A3 to create this fabricated EPD. So it is a little confusing if you just pull two things up side by side to compare. So that's why the takeaway here is read through the EPD. But I also just want to point out, when Shana pulled up all those different numbers, it is, as she mentioned, like sheet that becomes HSS, if you are getting it from a blast furnace, will have a higher GWP. Nucor does produce all of our steel through EAF, so that number is lowered. But as you go through your embodied carbon analysis, it's important just to make sure you're looking at the quantity of steel you need, whether it's HSS or wide flange, and multiply that through to get your true embodied carbon content, and not just your your unitized number, because you might not need the same amount of HSS as you would for wide flange for the same application. So overall, hopefully, I hope this helps shed some light when you're digging into steel EPDs. And I think that's what we have for today. So I think the slides will be available, but again, I'm joined with Ken from the Nucor Seattle plant and Raleigh from corporate. We also will have on the line for questions later Patrick and Chris. They are environmental engineers at the mill as well. So happy to field questions for everyone later. Thank you.